Hi everyone, so we are now on lesson 4 lenses, which is going to be our last lesson in the Light and Optics unit, at least the last part on video. Learning goals here, we're going to be looking at converging and diverging lenses, so two different types of lenses. You'll need to know how they're different. And then we're going to draw more ray diagrams, and we're going to use SALT. So this is going to look a little similar to what we did with mirrors, except now we're applying the ideas to lenses. So you've definitely heard of the term lens before, as in a camera lens, right? Or the lens on a microscope. So the objective lenses, for example, if you were ever learned the different parts of a microscope, you might have learned about the objective lenses. And so this is a ray diagram for a lens, so that's where we're going to be headed. So what is a lens? It's a piece of transparent material that refracts light. So that's kind of a general definition for it. There is a weird way of having a lens that actually doesn't, that isn't composed of material in this such a way, which I'll maybe get to at the end, which is kind of interesting. But in any case, the ones that we're dealing with are going to be made of transparent material, usually glass. Okay, so there are two main types of lenses that we're going to cover. We have converging lenses, which are sometimes called biconvex lenses. So if you remember from mirrors, right, the convex shape, if you were standing on this side of the mirror, the convex shape, it bends sort of so that the middle bulges towards you if you were standing here. So you can see that this is convex, like a convex mirror. It bulges towards you. But it's biconvex because if you were standing on the other side of the lens, you would see the same shape. So you have a convex shape on both sides. So we call this a converging lens because if you have light rays that go into it, they converge on a focal point. So meaning converge meaning come together. So they gather light, if you like, and put it into one place. Magnifying lenses are examples of lenses that do this, which is why maybe if you've ever watched cartoons, they sometimes show you burning paper because it focuses all the sun rays on a single point, which can make it quite hot. I've never actually tried this, but I have seen that this potentially can work. So I wouldn't do it. It's probably pretty dangerous. Diverging lenses. So diverging lenses are biconcave. So remember concave mirrors where the outer points bend towards the person there. So it's like the C, where the outer parts of the C bend towards you. And so you have that on both sides. So we call that biconcave, right? Remember bi means two, so biconcave or biconvex. And these are diverging lenses. So diverge means send on different paths. So if you have light rays that are parallel to the principal axis going through a diverging lens, they will diverge, right? They will separate. But they will separate in such a way that if you were to extend those rays backwards in a straight line, they would all go through the focus on the other side of the lens, right? The side of the lens that the light's originally coming from. So here rays parallel to the principal axis will converge on a focal point on the other side of the lens. Here they will diverge, but they can extend virtually back to a focal point on the same side of the lens. An example of where you might find a diverging lens, I wear glasses, I'm nearsighted. So if you are nearsighted and you wear glasses, then your glasses will be diverging lenses. So they essentially the issue is if you're nearsighted, your eye is too long. And so when the lens that's in your eye focuses the light on your retina, which is what you use to create the image that will pass to your brain. If your eye is too long, then the focal point is in front of the retina. So what a diverging lens will do is it'll push the light rays apart so that essentially your eye, the lens in your eye, when it actually tries to get those to focus on the focal point, because the light rays have been pushed apart, the focal point is pushed back. And so it goes onto your retina, and you can see normally when you're wearing your glasses or your contact lenses. Okay, so by the way, if you're farsighted, your glasses would be these. Okay, so it would do something similar because your eye would be too short, and so the focal point is behind the eye. But the converging lens causes the light rays to converge more sort of sooner, and so they'll converge earlier and hit the retina in that case. Okay, Images produced by lenses. So we're going to use the same techniques we use for mirrors. We're going to use ray diagrams and we're going to use salt. But this is where I want to stop you and get you to think about what you're doing when you do these questions. Because what you'll often get in front of you is you'll get a picture that looks familiar to you, right? You'll have a principal axis. You'll have something in the middle of a principal axis. You'll probably have an arrow somewhere. You'll have C and F, and it will say draw a ray diagram. And you might think, okay, I know how to do that. And you'll remember doing that for mirrors. And then you might, as I've seen a lot of students do, draw a lens diagram, draw a mirror diagram for a lens, and get completely the wrong answer because lenses and mirrors are very different, right? Just think about them in real life. A hand mirror that you use in the washroom or somewhere to look at yourself versus a magnifying glass. They're very different things. You can see through this one, you can't see through that one. So make sure you realize what you're drawing your ray diagram for. If you're drawing it for a mirror, then it will be like the ones that we did previously, and what you'll notice is that in those ray diagrams, the light rays don't actually go through the mirror, right? Everything stays on the left-hand side of your drawing if this is a mirror. So if this is a mirror, everything stays over here. The only time you'll have something drawn on this side is if you have virtual rays, right? All the actual light rays stay on this side because they hit the mirror, and then they reflect. But for a lens, it's the opposite, right? When you have a lens, the light always goes through the lens. So you'll see light on the left, you'll see light on the right, and the only time you'll see sort of like a bouncing back is when you have it, like in this case, when it's virtual. So there's no real bouncing back. The light goes through the lens, the light bounces back off a mirror. So make sure you keep that in mind. Okay, one more thing to know before we get started on how to draw these ray diagrams. We're going to use a simple assumption here. It's a slightly incorrect assumption, but it doesn't introduce much error into your calculations. And it is an assumption that will just make your work that much easier. So really, when you have light rays going into a lens, refraction will happen twice. Because remember that refraction happens when you change media, when light goes from one substance to a different substance. So that's going to happen twice with the lens, because it's going to happen when the light travels from the air to the lens, and then it's going to go through the lens, and then it's going to move out again, right? It's going to move from the lens to the air. So you'll see it refracts twice. But the way that we're going to draw these diagrams is as if they refract only once in the middle of the lens. And if the lens is thin enough, this doesn't introduce much error into your drawings, and it makes them easier. So that's what we're going to do. Okay, rules for drawing ray diagrams with these thin lenses. So if you've got a converging lens, there are 3 rules here. All rays parallel to the principal axis go through the lens and refract through the focus. So if you got a line that's parallel to the principal axis, then when it hits that lens, it's going to hit the middle, and it's going to bend, and it's going to bend so that it goes through the focus on the opposite side. All rays that pass through the focus and hit the lens go through it and then refract to become parallel to the principal axis. So it's kind of like the reverse of what we just said. If you've got a light ray that goes through the focus and hits your lens, when it bends, and when it refracts rather, it will bend parallel to the principal axis. So it's kind of the opposite counterpart to that red one, right? It's through the focus and then goes straight. Finally, all rays that go through the vertex continue in a straight line without refracting. So this line, if it goes through the middle here, just make one straight line. It just continues to go through. Okay, so those are your rules that can help you draw ray diagrams. So we're going to start looking at the different cases, and you'll notice that there are the same number of cases for converging lenses as there are for concave mirrors. You've got your 5 cases. So in the first case, what happens if you have an object that's outside of C, which remember C and 2F are the same. So outside of C. Well, if we follow our rules, right, we have a light ray parallel to the principal axis. That's going to go through the focus. We have a light ray that goes straight through the center, and a light ray that goes through the focus. So it's now going to bounce back and become parallel to the principal axis. Where do all those rays intersect? They intersect there, so that's where our image is going to be. We classify it according to SALT, then it's smaller. Right? The image is smaller than the object. It's inverted, it's upside down. It's between F and 2F, which remember, we also call C, so it's between F and C. And it's a real image because the light rays actually do cross there. So just to show you very quickly, if I was going to draw this, I would start from the top here, and I would draw a light ray that goes straight. into the center of the lens. Then I would draw a light ray from there that goes through the focus, because that's my rule. I could draw a light ray through the center if I wanted to. That would be good enough. I only need 2. I could draw 3, but I only need 2. And so this is where my image will be, right? It's going to be upside down, so it's going to be somewhere here, where those two cross, right? So if the top of this is where those 2 light rays cross, then the top, where those 2 light rays cross will also be the top. And so you'll notice that, right? I get an image between F and 2F that is smaller than that image. It's upside down, but the light rays really do cross there, so it's real. Okay, case 2. What if you have an object at C? So just ignore all this stuff here. There are math equations associated with these ray diagrams that we're just going to skip because we're a little short on time for this course. But case 2, what happens when you're at C? So when you're at C, we apply the same rules, right? Parallel to the principal axis, hits the mirror, goes through the focus. And they use their second line as going straight through the center. And when you actually create your image on the other side, you will notice that it's the same size as that one there. It's at C. So again, some commonalities with mirrors here. It is inverted, and it is also real. Okay, so the light rays really do cross. Case 3. What happens if your object is between C and F? So same rules. So hits the mirror, hits the lens rather, and then goes through the focus. You can go straight through the center or go through the focus and then go parallel to the principal axis. All 3 rays will intersect at this point. You draw your object, and you'll notice that it is larger than your original object. Your image is larger than your original object. It is still inverted. It is beyond 2F, and it is real. Okay. Case 4. This is very similar to the case when you've got an object at the focus when you have a mirror. If it's at the focus, then what's going to happen is your light rays that emerge on the other side of the lens are parallel. So this one that goes straight through the center and this one that goes through the focus, they're parallel, so they're never going to intersect on this side. If you extend them virtually behind the lens, they're never going to touch on this side, so you just don't get an image. So there's no image to perform salt on, so we leave it at that. Final case for a converging lens. What if you've got an object in front of the focus? Okay, so a ray that goes through straight to the parallel to the principal axis will continue to go through the focus on that side, so that's easy. You're going to have this one that goes straight through the middle. That's going to do the same. It's going to be difficult to actually go. You can't go forwards and go through the focus. So if you're planning to have a light ray that goes through the focus to go straight, you're going to have to extend it backwards from the object. And then if you do that, you can apply the same rules. This will go straight. So these light rays are diverging on the right-hand side here, right? They're not coming closer together. So you have to extend them behind the lens to see where they will virtually touch, and that's going to be here. So your image is actually going to be there. It's going to be larger than your original object. It's going to be upright. It's on the same side of the lens as the object. And of course, these light rays don't actually cross. They're extended backwards, and so this is a virtual image. It's not produced from the actual crossing of light rays. All right, one more thing to cover. Diverging lenses. So we have our own set of rules for these, but you'll notice that they're related to the rules for converging lenses. This should say diverging. So all rays parallel to the principal axis go through the lens and refract such that if you extend them backwards, they go through the focus virtually. So in other words, when light rays go through these lenses that are shaped like this, they don't come together, they go apart. So if you've got a light ray going parallel to the principal axis here, it's not going to go towards the focus, it's going to go away from it. But in going away from it, it actually goes virtually through the focus that's on the same side as the source. So it goes backwards through the focus virtually. All right, same for this green line here. So this green line, if there was no lens here, this green line would go through the focus, which if we know for a converging lens, if it goes through the focus, it will then go parallel to the principal axis. So this would go through the focus, but it doesn't. So because it would go through the focus, though, that now goes parallel to the principal axis. So you could, if you wanted, put a dotted line here showing it going through the focus, but you don't need to. The red line is the same for both types of lenses. Any line that goes straight through the middle will continue on, and you won't see any refraction. Okay, let's apply the rules. There's only one case for diverging lenses, so we're going to see this same picture. So because the light rays diverge on the right-hand side, they're not going to create an image on that side. The image is going to be on the left as the same side of the object. So this line that goes virtually through the focus, we can extend it backwards. And there are some actual light rays where we will have them cross. So this red ray is real, but this blue line here, the extension there is not real. And in fact, generally speaking, the extensions here are not real. And so this image is actual virtual, right? So just because you have one red line here doesn't make it real. The actual crossing of the light rays is virtual. There's no other light rays that are actually crossing here. So it's a virtual image, it's smaller, it's upright, and it's on the same side as the lens. So you might notice that anything that's on the same side as an object, any image that's on the same side as an object, is a virtual image. So the last thing I wanted to mention, which I forgot to put in the presentation, so I'll just Google it for you, is can you have a lens without this kind of material? So it turns out you can. So there's something called an Einstein ring, which is very weird. And that's it there. So what you can have happen is if you have an object in space that is extremely massive, that's in sort of front of this object that's behind it, what happens is the light from the object wants to go straight out in all directions. So it wouldn't be coming to Earth, it would be heading out in all directions. But this massive gravitational object here curves space and bends the light like a lens, so that the light from this object behind this other object here bends in all directions and you see it as a ring. But actually, if you were to see, well, I mean, this would be in the distant past, so nothing would be there now like it is today, like you would see it. But if you were able to figure out what this was like, billions of years ago or whatever, then this would be behind the point in the middle as sort of like a single galaxy, but it looks warped because this object's gravity has bent the actual light. So that's kind of cool. Just one other quick thing to mention there, because it's a common misconception that bugs me that people have. If you look at the stars in the sky, most of them are not dead. Almost all of them, and probably even all of them, are there. Stars in our galaxy are not that far away, in the universal scheme of things, maybe a couple thousand light years. But generally speaking, all the stars that you see in the sky are just a few light years from us, up to a couple thousand. So anyways, that's not really relevant, just because that bugs me. All right, have a good day.